point out the units and everything to once, well, if you didn't have me for Chem 20, then you don't know that I harp on unit analysis all the time. But unit analysis works, once again, just by manipulating the units, we can show that energy is related to Gibbs free energy, or the E for the cell potential is related to Gibbs free energy, and it's related by this relatively simple equation compared to the rest of the other stuff that I did. So N is the number of moles of electrons that are from the balanced chemical equation. F is Faraday's constant, which I'm going to give you Faraday's constant, because what is it? 96,485. And then E cell is your standard cell potential, like we were calculating before, cathode minus anode. Okay. Right. So then, of course, the next thing is to actually use it. So using tabulated electropotentials use the potentials to calculate delta G for the reaction. So our equation, delta G0 is equal to negative N F E cell standard conditions. So again, I like more and more to write these out as half reactions. So starting with the sodium, going to Na2, not Na2 plus, 2 Na plus 2 electrons. All right, if we have 2 sodiums and we get 2 sodiums with positive charges, there has to be 2 electrons. And then the other one can be a little bit harder to see. But remember, right, H plus OH minus is H2O. So there's kind of hidden in here the fact that there's 2 hydrogens from the water that are being reduced. 2 hydrogens from the water that are being reduced to make the hydrogen on the other side. So I guess I said it already, but which one's being reduced? Hydrogen. So hydrogen's gaining 2 electrons. You gotta read these from left to right. Hydrogen gains 2 electrons to become H2. So if that's being reduced, is it the cathode or the anode? Cathode. And then that means that this other one is being oxidized. It's losing electrons. And then that's the anode. So reduction potential for the cathode, it's an easy one. It's the standard hydrogen electrode. So it's on the chart, but it's 0. And then the oxidation, and again, we're going to write the standard potential here. So sodium is negative 2.71. So our, not delta, our E cell naught is going to be equal to the cathode minus the anode. So 0 minus a negative 2.71. So E cell naught is a positive 2.71. And then delta G naught is equal to negative N is the number of moles of electrons. So how many moles of electrons are being reacted or participating in the reaction? It's 2. 2 moles of electrons, which is the other nice thing about writing out the balanced, or writing out the half reactions, because you can see those electrons. So it'll be 2 moles of electrons times 96,485. no, wait, that's, yeah, joules per coulomb times wait, I think I got the units wrong for Faraday's constant. Coulombs per moles of electrons. Volts is joules per coulomb. So then delta G, standard conditions, is whatever that is. Negative 1, 2, 3, 4, 5. Negative 5.23 times 10 to the 5 joules. Put this back into scientific mode. All right, so plug it in. And then just thinking about this also conceptually, it makes sense that delta G is negative because our E cell is positive. So if the E cell is positive, that means it has to be spontaneous. So then delta G should be negative. We haven't talked about the relationship of K yet. Okay. Oh, we kind of did. All right, so then K should be greater than 1. There, now we're recording again. So this next question is asking, right, if one of them is more electronegative, does that explain it? So which of them, I2, is iodine or bromide more electronegative? Bromide, right? Getting close, fluoride's the most electronegative. As you get closer, you get more electronegative. So it can't be B because iodine is not more electronegative than bromide. It's bromide that's more electronegative. And so in this reaction, Br minus already has the extra electrons. So if it's more electronegative, it's not going to give up its electrons to iodine and be oxidized. So A. Okay. Moving on. So we go back to this triangle actually. All right, so we did this delta G to E cell. Delta G equals negative NF E cell. Right, we filled in that link. Now we're going to talk about how E cell is related to K, or the equilibrium constant. So we're going to kind of do this in a roundabout way because we know that delta G is related to K, and it's this negative RT ln K. And we know that delta G is also equal to negative NFE. So we can make NFE equal to negative RT ln K. I think it's the identity property. Look at that, math stuff. So then we can rearrange all of this to say RT over NF times ln K. All right, because the negative NFE and the negative RT, those negatives will cancel out. And then a bunch of these are constants. So R is a constant. Under standard conditions, which is what we're talking about here, again, this little 0 or naught, sometimes it's called. So E cell naught or E cell 0 at standard conditions is always going to be 295 degrees Kelvin. F is Faraday's constant, so that's always constant. And then the last thing that they throw in here isn't, well, I won't say it's not necessary. I don't know why it is necessary if it is. But they convert the natural log of K to the log of K, which is fine, and it kind of makes this a larger number so it's not so small, but you don't necessarily have to do that. Yeah, as far as I could find. If you want an equation to just memorize, though, you can just memorize this one. If you have no problem with the constants being in here, you can always use this and plug constants in. This also includes the temperature dependence. Although I guess we'll have to talk about that more. So E cell then can be related to K through this 0.0592, and this is volts. It's not another constant to fill in. It's not volume. Those are just the units. So it's volts divided by N, which is the number of electrons, times the log base 10 of K. So we can use these standard electrode potentials to calculate K for the oxidation of iron by hydrogen. It's always nice when it's hydrogen, because we know that cell potential is going to be 0. So starting off here, what would the two half reactions be for this iron being oxidized? Oh yeah, 2Fe. Don't want to forget that. Yeah, plus 6 electrons. So in the other one, and conveniently we're told that it's being reduced by H+, but H+ is also specifically written out. We could just say 6H plus 6 electrons will give us 3H2. And since we were given a balanced chemical equation too, if you can't figure out the number of electrons on one of the half reactions, do the other half reaction, and sometimes that'll be easier. It's like this first one with the iron, pretty easy. It goes from 0 to 3+. There's 2 of them, that's 6 electrons. And then because it's a balanced chemical equation, this has to also be 6 electrons. This kind of fills in that blank for you. So which one is being reduced? Which one's gaining electrons? What? Hydrogen, yeah, H+. So this is being reduced. That also makes it the cathode. That means that iron is being oxidized, which makes it the anode. And then cell potential, or the half potential for this is going to be 0. And then E anode for iron is going to be negative 0.036. And so it's going to be cathode minus anode. So 0 minus a negative 0.036. So E cell is equal to a positive 0.036. Now we can use our new equation for delta G, standard conditions. Oh, sorry, no, other one. Because we want to use E cell equals 0.05, it's 592 over N times the not the natural log, the log base 10 of K. So the last thing that we're missing is the number of electrons. How many moles of electrons participate in this reaction? 6. Right. Another benefit of writing out those half reactions is it tells you how many electrons are reacting. So 0.036 equals 0.0592 over, not 2, 6 moles of electrons times log of K. So 0.036 times 6 divided by 0.0592. So 3.6486 equals log base 10 K. So 10 raised to that number will give us 4.45 times 10 to the 3 equals K. This chapter's just rife with equations. Okay, so this is what I recommend you memorize and then write down at the very beginning of the exam. So the relationship between delta G and E cell, delta G equals negative NFE. The relationship between E cell and equilibrium is E cell equals 0.0592 over N, moles, which is the moles of electrons, times log base 10 of K. And then we can also go from K to delta G. So you could, there's no, sorry, I was trying to think of a situation where you could have E cell but not be able to go straight to G. But you always can go either from E cell to G or from E cell to K. I don't think there's a situation where you'd have to go from E cell to K, then K to delta G. All right, so that's the relationships between all of those. So if a redox reaction has an equilibrium constant of 1.2 times 10 to the 3, which statement is true regarding E cell and, gives free energy, delta G, and E cell for this reaction? So K is a large number, and specifically K is larger than 1. Because if K is equal to 1, then this log of K and the natural log of K would both be 0. So if it's greater than 1, so if K is greater than 1, then the log or the natural log will be positive. If K is less than 1, then the log or the natural log of K will be negative. So with that in mind, is E cell, well, okay, I'll ask it this way. Is E cell going to be positive? Yep. All right, because this would be larger than 1. And then is G cell going to be positive? No, it'll be negative. So E cell, positive, G cell, negative. And those things always have to be opposite signs because otherwise you did your math wrong. Because they're both predicting the same thing, but you predict it with opposite signs for them. So positive voltage means spontaneous. Negative change in Gibbs free energy means spontaneous. Can't have a negative voltage and a negative change in Gibbs free energy. All right, so that's all for standard conditions. Of course, most things don't take place at standard conditions where everything is 1 molar in the concentration. So what happens then if the concentrations are different? and you might be tempted to just swap K out for Q. That doesn't quite work. That only tells you how different it is from standard conditions. So what actually happens is as those concentrations change, of course, your voltage is going to, well, over time your voltage will drop, but here we're written with different standard conditions where we can actually increase the voltage by having a higher concentration on one side and lower concentration on the other. Right? So we're skewing that reaction by skewing the equilibrium, or getting farther away from equilibrium. So, okay, this derivation's kind of crazy. So delta G at standard conditions is equal to negative NFE at standard conditions. Delta G at non-standard conditions is equal to negative NFE at non-standard conditions. So we can plug the same equation in here for both. So it's negative delta N, oops, wait, no. That's not what I wanted to do. This is negative NFE. I'm going to leave the cell off. And negative NFE naught plus RT ln of Q. And then algebra hacks, we're going to get NFE plus NFE standard conditions equals RT ln of Q. And then because we did that, we can extract the NF from this and get, negative. We'll extract the negative with it too. So it's going to be E minus E naught equals RT ln of Q. So then E minus E naught equals negative RT natural log of Q, and then this is over NF. And then we could say, I'll move this up here, E is equal to E0 minus RT over NF natural log Q. It's just a lot of algebra. Very conveniently, though, has a very similar format, convenient or inconvenient, has a very similar format to delta G equals delta G 0 plus RT ln Q. And in essence, they're doing the same thing, but we have to use slightly different numbers because we're talking about slightly different quantities. So essentially what each of them does is tells you how far away you are from standard conditions, right? Takes your standard conditions and modifies it either in the positive direction or the negative direction, which is why the natural log is very convenient, because the sign can change depending on whether you're higher or lower than 1. Okay, but RT over NF should look familiar. It's a bunch of constants again. And so we can collapse that down into the 0.0592 volts over N, which is again the number of moles of electrons that are being transferred. So now our E cell at non-standard conditions, this is all still at 25 degrees C, or 295 or 298.15. But now we can use non-standard concentrations. And there's a couple special cases. So just like for delta G equals, delta G standard conditions plus RT ln Q. Okay, so there's special conditions when, make sure the microphone's on. There's special conditions when something like K is equal to Q. If you remember for this equation, when K is equal to Q, then delta G at non-standard conditions is 0. The same thing applies here. We'll kind of get to those. All right, so this is the Nernst equation that you can use to calculate cell potentials at any concentrations. Okay, so determine the cell potential of an electrochemical cell based on the following two half reactions. And for once, we're given them as the oxidation and the reduction half reactions. But that means that we have to combine them together to get the full reaction, and it's not balanced. So why are these two half reactions not balanced? What's missing? Spot the difference. They have different numbers of electrons. Right, so we gotta have the same number of electrons. So we're gonna have to take the second one and multiply all the coefficients by 2 to get the right number of electrons. This is gonna be 2 VO2 plus 4 H plus 2 E minus 2 VO2 plus. That's a 2. H2O. And things like this are important. That's a liquid. All right, so since we're at non-standard conditions, we need to use the Nernst equation. So our E cell is going to be E cell naught minus 0.0592 over, I'll just do N, times, and then this again switches, it's the log base 10 of Q. So how do we calculate Q? Products over reactants, yes. Concentrations of the products. And so we're going to have things like nickel 2 plus times H plus. Oh, wait, no, H plus is not a product. Only other product is going to be VO2 plus squared. So VO2 plus has to be squared because there's, multiply the whole thing by 2, so we got to raise these each to the exponent of their coefficient. So then our reactants are VO2 plus squared, oops, and then H plus to the 4th. And that's going to be 2 squared times 2 over 0.01 squared times 1.0 to the 4th. So 2 squared times 2 divided by 0.01 squared by 1 point, well, to the 4th. So you get 8 times 10 to the 4. And then we also need to find E cell. So we got nickel, 9. Where'd it go? I just had it. So nickel is negative 0.23. And this vanadium, whatever it is going to be 1.00. So which one's our cathode? the vanadium, the reduction reaction. So then, trying to leave space down there on the left. So our E cell standard conditions is going to be cathode, 1.00, minus the anode. The anode is negative 0.23. So then that ends up being plus, so 1.23. So E cell equals 1.23 minus 0.0592 over the number of electrons, 2, times the log of Q, which is 8 times 10 to the 4. So before even typing anything in, I think E cell is going to be positive or negative? Should be positive. Could be positive. Could be negative. So 1.23 minus, well, in this case it could be negative because the log base 10 of 8 times 10 to the 4 is going to stay positive. So it's going to depend on whether this portion is larger than 1.23. If K here was less than 1, then that would make this portion negative, and then this would have to be positive. Divided by 2 times the log of 8e to the 4. Oh, but also, well, no, because we're doing it for non-standard conditions. So E cell at the non-standard conditions equals 1.08 volts. So it did stay positive. Even though, so, and the other thing that would suggest is probably going to be positive, right, is because this, our E cell not ended up being positive. But that's the thing about non-standard conditions. And actually, I think this next one, no, it's the one after. These are just the electropotentials. Okay, well, we'll get to it. There's some weird stuff that can happen at non-standard conditions. So these are those special conditions that I was talking about, though, where, right, if you have Q is equal to 1, then E cell is equal to E cell standard conditions, right? Because if Q is 1, then you're at standard concentrations of 1 molar for everything. If Q is less than 1, then you have high reactant concentrations, which will drive things to the right. Also, as I mentioned, right, if we plug in some number for Q that's less than 1, then this becomes a negative, and then it's a negative times a negative. It has to be positive. So it'll get more positive. If the opposite case is true, right, if Q is larger than 1, then you have higher product concentrations, and it'll drive it to the left. So like the example we just did, our E cell at the non-standard conditions, that voltage was lower than at standard conditions. And then at equilibrium, the reaction has no tendency to occur in either direction, and that's the other special condition to remember. So E cell standard conditions equals 0. I think that might be I think that's a typo, actually. Because it's E cell, and then it would be E cell this minus so when you put K, yeah, because if you put in K here, then you get this, because we're E cell not no, so I'm thinking of the RT null and K. Yeah, this one. Right, because E cell naught is equal to 0.0592 n times the log of k. So this is a typo on this slide. It's E cell at non-standard conditions is 0 because this equals this. So those two things will cancel out. All right, so having gone over that though, in an electrochemical cell, Q is 0.001, K is 0.1. What can you conclude about E cell and E cell 0? So it helps a lot for these kinds of problems to just write out the equations. It's like, so how would you calculate E cell from Q? Right, E cell at non-standard conditions. What would be E cell 0 minus 592 over n log of Q. So if I put in this number, 0.001 in for Q, what does that mean that E cell at non-standard conditions has to be? It can only be positive or negative. It has to be one or the other. You could also just type into your calculator, right? So what is the log of 0.001? Type it in. See what happens. What is it? What? Negative. Yeah. So if I take that negative number from this, it ends up being -3. -3 times negative 0.0 whatever, doesn't matter. There are two negatives, so it has to be positive. So no E cell has to be positive. So it's either A or it's C. And then we could calculate E cell 0 as 0.0592 over n log of k. So again, right, if you plug in 0.1 for k, is it a positive or a negative number? Negative. If you plug in any number less than 1, it'll be a negative number. So so E cell has to be positive, E cell standard conditions has to be negative. So this is also a situation where we can have positive E cell, which means that it's spontaneous, even though under standard conditions, it would be non-spontaneous. So this is what I was thinking of earlier. You can actually have a cell that's a spontaneous reaction that's made of copper and copper, just because the concentrations on either side are different. You can create enough of a difference to cause a spontaneous reaction. So on the left side, we have 2 molar copper. On the right side, we have 0.01 molar copper 2 plus. So this is going to be, well, just for kicks, let's do the E0, right, the standard conditions. So E cell 0, and it's copper, this one. So right, copper's both our cathode and our anode. The reduction potential is 0.34, so that's the cathode, minus the anode, which is 0.34. I don't know why I wrote 5. So 0. So then when we calculate the cell potential, though, for this specific non-standard situation, E cell at non-standard is going to be equal to 0 minus 0.0592 over 2 electrons log of, and then it's going to be Q. So products over reactants So is Q going to be larger or smaller than 1? More or less than 1, maybe is what I should say. If I take 0.01, I divide it by 2, it's just going to make it smaller. So the log of that. So E cell is equal to 6.81 times 10 to the negative 2 volts, but it's still a positive number, even though it's a small one, so it's still spontaneous. So even though we have copper and copper, they still react. And so you would see that small voltage if you set up this system. So by equalizing, well, it's almost like an osmosis effect where there's a really high concentration on one side and a low concentration on the other side. Or I did that backwards. High concentration, low concentration. Those concentrations want to equal out. You could also say that it's increasing the entropy by spreading out the copper 2+ ions. So. Okay, well, we'll leave off there.